next, I'm going to talk about our latest hybrid simulation tools, and especially our progress to move to hybrid simulation to other areas other than civil structure. Yeah. So a little bit of background information, and then some new tools in wind energy, aerospace, automotive, and some virtual testing methods, and some model-assisted testing method. So we have talked a lot about the hybrid simulation method, and started from structure, earthquake simulation, and now it's migrating to other areas. And so definitely we have seen this one a few times, and it starts with earthquake simulation, structure, and a lot of applications in civil structure. And then around the year 2000, this method starts to migrate to other industry. For example, this one, ground vehicle. So in this application, so MTS worked with Nissan Motors. So this Nissan Motors wants to design the damper system. Those are the active damper systems. So meaning that the damper properties will change depending upon the vehicle condition, vehicle speed, and all those things. So the damper property will change based upon the CAN bus information it receives. So the test system got to be connected with the vehicle, the computer inside the vehicle. And so to test this kind of active system, usually Nissan Motors, put them onto the car and drive around and feel it, and then take back and then adjust the opening, valve opening, or other things. Then put on the car and then drive again, and so takes a long time to tune those dampers. So then we provided this kind of a hybrid simulation system. So the numerical substructures of the road, tire, and the cars except those dampers. And physical substructures are those dampers. So the model is run in this hill simulator display system, and a car sim is the software to simulate the car driving on the road, definitely with all those 4 dampers. So then the model is running here in real time and generated the command. Command is sent to the test rig again through SquareNet, and then move the actuators and move the dampers. Then the dampers send back the force, to the car sim model, and then it solves for another moment. So this is a real-time hybrid simulation application. Yeah. So this is a video. So now the car is running. So starting to turn, and then you can see the actuator starts to move, and feedback goes to the car model, and so in this case, the damper engineers, they don't need a car to tune those dampers. So they just need to, in this rig, and then tune the damper and hit run, and then run the simulation, and analyze the result, and then adjust the damper again. And so in here, very easily, they can tune the damper. And so this is an example of real-time hybrid simulation in ground vehicle. So another real-time hybrid simulation in ground vehicle we developed is this steering system, hybrid simulation system. So again, the physical substructure is here, the steering column and the rack, and so it's connected to MTS 5-channel test system. So again, you have a D-space, and there's a car sim model running, and then there's a roll tire, all those things, and then the vehicle generated command sent to MTS controller, so 5 commands sent to MTS controller, and move the actuators, and so you can in here you can turn the steering wheel, stuff like that, and put the human input or robot input in here, and then so this is again this is an active component. There's a electric motor system here. So electric motor system, it has a controller. So so that controller gets the command from the test controller as well. So drive that electric motor and provide the torque assistant. So so that's another real-time hybrid simulation system. So in here you can see there's a human input, and the car model is running here. So this is robot input here, and so this is the steering rack tie rod, and so this is a car sim model is running here. So this is another real-time hybrid simulation example. And another real-time hybrid simulation example in ground vehicle is this quarter car system. So 1/4 car is the physical substructure. Rest is the numerical substructure, and also so the tire handling get the 60F loading. So in this case, the tire is partially in numerical model. So the lateral force and the vertical force is obtained from this test rig, and the rest of the DOF load is obtained from this numerical substructure. So so this is so the suspension, quarter suspension is in the physical substructure, and then 2 degrees of the tire is the physical substructure. Yeah. So that's again it drives on the road and simulates all kinds of maneuvers, and then you can tune your suspension in this way. So this is the video. Start to bounce. Again, the numerical substructure, the model is running in the car sim, and the model is downloaded to a D-Space box, running. The model is sent through ScribeNet to MTS controller. Yeah, same approach. So that's real-time hybrid simulation in automotive, and then we have seen wind energy, people start to use hybrid simulation, and Shawn You has talked about this example, so I don't want to repeat. So in here, we developed a generic client element so that Open Fresco can talk to ANSYS, so that ANSYS can be used for hybrid simulation. So Shawn You did that, and now we see strong trend to use hybrid simulation in aero industry, and definitely our slow hybrid quasi-static or pseudodynamic hybrid simulation can be used to test part of the airplane, for example, a wing, and model the rest of the structure, and through same method like we talked about this morning. Yeah. So, and also definitely we can do real-time hybrid simulation. For example, this airplane, landing, and to test the landing gear, to test the damper in here. So we could model the airplane with a kind of software. For example, we could use Adams, and then the Adams will calculate the displacement, and then displacement applied to this damper rig, and measure the force and send back. So that's can be done, and in aerospace, a lot of times the models are very complicated. Like Shawn You mentioned, we could use a reduced order model so that the model can be solved in real time. And in ground vehicle, in aerospace, a lot of times people use software called Adams. And then so we want to use Adams to do this real-time hybrid simulation. So we need to connect the Adams with Open Fresco to do hybrid simulation. And same thing, we need to create a generic client element to send out the command to Open Fresco and get feedback from Open Fresco. So Shawn You created this generic client element and put it in Adams. And then, so now we can use Adams to do real-time or pseudodynamic hybrid simulation. So this is an example we did. A car, we just use a car, and then inside there's a spring, and then this spring is simulated by this machine, and then the car running on a cobblestone road, and then it could do the real-time hybrid simulation, yeah, using that generic element. Same thing. So we did another example. So there's a car model, not showing here, to show you the test rig, and the test rig has 24 actuators and 24 control channels, and so inside this car there's a spring, and represented by this column, and we use the Adams coupled with Open Fresco, coupled with this test rig to do real-time hybrid simulation. That worked well. Yeah. So that's hybrid simulation. So in other industries. So next, I'm going to talk about our modeling capability. So like I mentioned before, we could do virtual testing, build complicated models, and in Adams format, in ANSYS format, in OpenSys format, and we can also build our models in Simulink format. So we can model our servo valve and actuators and accumulators and controllers, controller, PID controller, degree of freedom controller, and the matrix controls, everything. inside our controller we can model. And so then we can build really complicated virtual test system. For example, this one. So this is our virtual model of this kind of test system. It has 24 actuators. It has a matrix control, a very, very complicated control. So has 24 actuators and servo valves. So all those things are inside this model. So the controller, it has 24 control channels, and all the control parameters, filters, everything is in here. We can model. And then, so the model sets the command to the 24 actuator models, has a servo valve and accumulation, all those things, hydraulic stuff, everything's here. And then the actuator model sends out the 24 forces. The 24 forces is acting on the vehicle. So that's the vehicle model. That's the Adams model. Adams model is like this. Adams model has all the mechanical parts, and then it exports this model to Simulink and become a block like this. So this is a really shrink down Adams model. So all the mechanical parts are modeled in Adams, and then during simulation, so the Simulink call Adams and then Adams solve, and then send back signals to Simulink, and the Simulink solve another moment. So this is a kind of a software hybrid. Yeah. So we could do this kind of modeling. Actually, this is this model we created, and we created a model like this because we want to use this virtual system to do RPC iteration, to reproduce the drive file, to generate drive file, and then we use the drive file directly in the test rig, so that we don't need to do RPC iteration anymore. And in ground vehicle, and to do durability test, to generate command, we have a software called RPC Pro. RPC Pro, based upon the desired file, and it does RPC iteration to find the correct command. Takes time, and so if we could use this virtual test system and use RPC to connect to this virtual system, figure out the drive file ahead of time, and then in the lab we will speed up the durability test significantly and avoid extra damage on the specimen during the RPC iteration. Yeah, so this is what we try to do. And also in aero, and we have a 4-channel system like this to prove our modeling capability. So we modeled this system, and the Adams model, and the Simulink model, and the controller, servo valve, actuator, everything, including this specimen modeled using reduced model approach. And then we compared our model with the real test. We played the sine wave and then sent the command to virtual system, to the real system, and compared the response. They match really good. And so what's our next plan for virtual testing? So we want to use virtual testing to help us to set up a real test. Use virtual testing to select the hardware, how big the actuator, servo valve, and accumulation, stuff like that. And we will use virtual testing to design the fixtures, and we will use virtual testing to predict the tuning parameters. And we want to use virtual testing to create drive files for real test. So that's our goal. So also, we want to do model-based compensation, like Shawn talked about, and I will not repeat. And also, we want to use string control in complicated tests. For example, in this aero testing example, the customers have this kind of a test system, and but they want to achieve some measured strings at certain locations, and then we want to find a method, create a method, so that our actuators can using actuators, and we can achieve the measured strings. So this is our plan. We are working on a method to do this kind of string control in aero industry. And so our thinking is, you have some string measurement. Those are the desired string states you want to achieve. And then in the lab, we have actuators and stuff like that to try to achieve those string states. So then we will characterize the string and the actuator input relationship first, using that relationship, and then generate a command, try the command, and find out error, and then change the command until the error becomes minimized. Yeah. So a lot of times, the test is done to validate FEA model. And FEA model, FEA can provide a string, field, distribution, plot, and you can find string for many points. And to compare the model with the test measurement, so we need to put many string gauges. And it's very time consuming. A lot of people tries to use digital imaging correlation system and to measure the string field. So in that case, in that case, the FEA result is a string field, and then the DIC system measures the string field as well. So then they can be compared, correlated, and so for that reason, so we are actively working with some DIC system vendors and connect our controller with the DIC systems, and to get the signals from DIC systems directly, and so can be compared with the FEA result. So we are actively developing that tool as well. So in summary, we see that integrating physical testing and virtual modeling is definitely a trend. And hybrid simulation allows only part of the structure to be tested and the rest of the part to be modeled. So, save you time and get a good result. Yeah. So we talked about that. And also, we are actively working on virtual testing and building all kinds of models, Simulink model, Adams model, and car sim models, and so that we can rehearse the physical test and help us to set up the physical test and get the command from the virtual testing. Yeah. And model-assisted testing is also very important, especially in aerospace. And so the model is running with the test and compensate for the test, and and provide string, provide optimization, provide string control, and it can do a lot of good things. And MPS offers all kinds of method, and our goal is to work hard so that you guys are successful. If you have a special need, let us know, and we will try to find a solution for you. Yeah. So that's the end of my presentation. Yeah. Question?
This atoms, is it based on rigid body dynamics simulation?
Yeah.
It's not a real finite element.
It's different from finite element. Yeah, different. Yeah.
So when we use hybrid simulation in civil structures, we have the equation of motion, and there are a lot of things that is going to be modeled numerically, and it's a complex system that we are trying to solve, and then the experimental element is subjected to complex boundary forces. But is that the case also in automotive and aerospace? Like, do we have to do hardware in the loop simulation for them, or we can just purely do cyclic testing and that would be sufficient?
So in the ground vehicle, and the use of a hybrid simulation, because a lot of active component, like the damper. The damper is not a simple damper, and damper property, damper has an adjustable valve. That adjustable valve got to get the command from the computer, a vehicle computer. The computer will, based upon the road conditions, stuff like that, and velocity, and then it generates a command for that damper, and then damper changes the property accordingly. So the damper property always changes, and then to do accurate test, so you got to implement that hardware, the computer inside the vehicle. So then, so you cannot do the simple block cycle, because your block cycle and the computer is not there, and you are testing the wrong conditions. So then you have to put the computer hardware there and generate the realistic command to the damper. And to generate that realistic command, you have to have the model and calculate the vehicle condition, calculate velocity, and stuff like that. And
so what we are testing is not only the response of the physical element, we are just testing the full cyber physical platform that is actually like working there. So exactly. It's not just to get the response of that damper, it's just to see if the full loop of the computer model and everything works together, because that's going to be eventually implemented in the vehicle. Exactly. Is that right?
Yeah, correct. Yeah. So,
All right.